Hello, my curious friend, and welcome to Deep Field Channel. Tonight we are going to explore the most honest distance the universe has to offer us, a number that seems simple on the surface, but conceals, the moment you try to cross it, one of the most complete and most demanding challenges any human being could ever imagine facing. A light year, but I promise to try not to make the subject so fascinating that it steals your sleep. Before we dive into this mystery, I would love to hear in the comments which corner of the world you are listening from tonight. And if tiredness gets the better of you, just leave a simple hello. It may seem like a small thing, but that tiny gesture tells YouTube that our space is a welcoming one and helps us bring more weary minds to unwind with us. If you enjoy our scientific journeys, please leave a like and subscribe as well. And to those of you who are already part of our community, thank you so very much. If you would like to feel even closer, consider becoming a channel member. Members get early access to videos before anyone else. The link is in the description. Now, wherever you happen to be, settle into a truly comfortable position. If sleep arrives, accept its invitation. Let us begin. Begin with the number itself. A light year is the distance light covers in a single year, travelling at 300,000 kilometers per second. Nothing in nature moves faster than that. Not particles, not energy, not information. This speed is not a record waiting for better technology to surpass it. It is a limit woven into the fabric of the universe since the moment of its birth, tested at every scale science has been able to reach, and upheld without exception at each one. A light year, therefore, is the distance you would cover if you could travel at the absolute maximum speed the universe permits, sustained for an entire year without stopping. That is the scale we are dealing with before we have even left our starting point. Most people picture the solar system as ending just beyond Neptune. Neptune orbits at roughly 30 astronomical units from the Sun, and the standard image of the solar system as a flat disk with 8 planets fits neatly within that region. But the solar system does not end there, not even close. Beyond Neptune lies the Kuiper Belt, a ring of icy bodies stretching from about 30 to 50 astronomical units. Pluto is a Kuiper Belt object. So is Eris. So is Makemake. And thousands of smaller bodies orbit silently through that frigid region. The Kuiper Belt gives way to the scattered disk, a sparse region extending several hundred astronomical units outward. And then, far beyond all of that, comes the Oort Cloud. The Oort Cloud is an immense spherical shell of icy bodies enveloping the solar system in every direction. Its inner boundary is estimated to begin around 2,000 astronomical units from the Sun. Its outer edge stretches to perhaps 100,000 astronomical units, possibly even farther. This is the region from which long-period comets originate, bodies with orbital periods of hundreds, thousands, or millions of years, disturbed by gravitational encounters with passing stars and nudged inward toward the solar system on elongated orbits. When a spectacular comet sweeps through the inner solar system, it has typically fallen from the Oort Cloud on a journey that carried it from perhaps 50,000 astronomical units down to just a handful of astronomical units from the Sun. 1 light year expressed in astronomical units equals 63,241 astronomical units. That places the outer edge of the Oort Cloud at approximately 1 light year from the Sun. The solar system does not end at Neptune. It does not end at Pluto. Its gravitational reach and the population of bodies bound to it extend to roughly 1 light year. The first 1 light year journey from Earth is, in a very real physical sense, a crossing through the outermost territory of our own solar system. You would not cross it and arrive somewhere new. You would cross it and arrive at the boundary between the Sun's domain and the true void. At the outer edge of the Oort Cloud, looking back, the Sun is still the brightest object in the sky, still clearly identifiable, still gravitationally dominant over everything around it, but distant, 63,000 times farther away than Earth is from the Sun, a point of light, not a disk. And looking forward, in any direction other than toward our own Sun, the nearest star systems are still more than 3 light years away. The emptiness between us and them belongs neither to the Sun nor to them. It exists because stars are rare, space is vast, and the universe was built in these proportions. The question is not merely how far a light year is. The question is what happens to you when you try to cross it. What happens to time? What happens to the body? What the ship around you is experiencing at every moment. How the universe looks from inside something moving fast enough for the physics to truly matter. The answers are strange. Some of them are genuinely unsettling, and none of them are intuitive because nothing in everyday life prepares a mind for speed at a significant fraction of the speed of light. The human brain evolved on a planet where the fastest things moved at a few kilometers per hour, and the physics relevant to survival was entirely Newtonian. The universe beyond that is genuinely something else, and travelling a light year is an encounter with that otherness on every level at once. There is a strange asymmetry running through this entire conversation. We can calculate every detail of this journey with extraordinary precision. We know how much time dilates, we know what the sky will look like, we know the radiation dose per month, we know the energy cost for every kilogram of payload, but we cannot make the trip, and that asymmetry between precise knowledge and practical inability is, in itself, one of the most revealing things science has ever produced, because it shows how far thought can reach when guided by honest physics, and it shows with equal clarity how much still separates thought from action. The average distance between stars in our cosmic neighbourhood is about 4 to 5 light years, not in every direction. The galaxy is not uniformly distributed. There are denser regions and emptier ones. Star-forming regions can have separations of a fraction of a light year. Globular clusters pack hundreds of thousands of stars into a much smaller volume. But in the local stellar neighbourhood, the region within a few dozen light years of the Sun, 4 to 5 light years between neighbours is roughly the average. This reveals something about the physics of star formation. Stars form through the collapse of molecular gas clouds. Those clouds fragment as they collapse, with each fragment producing a protostar. The scale of fragmentation is determined by the physical properties of the cloud, its temperature, density, and the strength of its magnetic field. The typical separation between the resulting stars reflects those initial conditions. The universe created stars at the scale and density that the physics of cloud collapse produces, not at a separation convenient for biological beings, not at distances where interstellar travel would be routine. At the separation physics dictated, and physics dictated separations of light years. It is worth pausing for a moment simply to feel what this number is: 1 light year. The distance that light, moving at 300,000 kilometers per second without pause, covers in 365 days. If you expressed that distance in kilometers, the number would have 19 digits. No everyday notation conveys this honestly. Our minds evolved on African savannas where the longest distance relevant to survival was a few kilometers. Physics allows us to calculate with precision what that distance demands. But feeling the scale, the intuitive presence of what a light year means, is something different from calculating it. That is why the numbers need to be translated. 15,000 years at the speed of our fastest spacecraft. All of recorded human history, plus 10,000 years left over. And still just 1 light year. When someone looks up at the night sky and sees Proxima Centauri, the nearest star, they are seeing light that left there 4 years and 2 months ago. That is what the closest neighbourhood looks like. 1 light year is merely the very beginning of that distance. The highest speed humanity has ever achieved with a spacecraft was reached by the Parker Solar Probe, which at its closest approach to the Sun reaches about 700,000 kilometers per hour. That is extraordinary by any human standard. At that speed, you could cross the United States in under 2 seconds. You could orbit the entire Earth in roughly 55 seconds. It is the fastest object humans have ever launched, and it is nowhere near enough. At that speed, crossing a single light year would take more than 15,000 years. The entire span of recorded human civilization fits within that travel time with more than 10,000 years still to spare, 15,000 years at our maximum speed to cover 1 light year. The gap between what we can do today and what the universe demands is not a gap. It is an abyss. To cross a light year in any span of time a human being could survive, you would need to travel at a substantial fraction of the speed of light. At 10% of light speed, the trip takes 10 years as measured on Earth. At 20%, 5 years. At 50%, 2 years. At 90%, about 13 months. At 99%, just over 12 months. These are the speeds where the physics starts becoming genuinely strange. And strange is an understatement. The acceleration phase is where physics presents its first demands with clarity. Before talking about what happens once you're at cruising speed, you need to understand what it takes to get there, because the journey begins long before the actual departure. It begins in the phase where the ship must gain speed from rest, accumulating the kilometers per second that over days and weeks will become fractions of the speed of light. And every second of that acceleration tells a different story about the boundary between what physics allows and what engineering can build. From the moment of departure, every second of thrust consumes energy at a rate the ship's systems must sustain continuously. Going from 0 to 10% of the speed of light in a few hours is impossible in the way it sounds. The forces involved in high acceleration would destroy both the structure of the ship and the people inside it. A sustained acceleration of 1g, identical to the gravitational pull at Earth's surface, would be physiologically ideal for the crew. It would simulate normal gravity throughout the entire acceleration phase without requiring a rotating habitat. The cardiovascular system stays conditioned because it still works against an effective pull. Bones remain loaded because the crew is effectively standing in 1g. The vestibular system functions normally because there is a consistent sense of up and down. At that 1g acceleration, the times required to reach significant fractions of the speed of light are calculable. Reaching 10% of light speed from rest takes about 35 days. Reaching 50% takes about 201 days. Reaching 90% takes roughly 730 days. Those are manageable timeframes. The problem is not the duration of acceleration, it is the energy it demands. For a hypothetical crewed ship of 1,000 metric tons, which is a conservative figure for something that must carry everything a crew needs for years, sustained 1g acceleration for 1 year requires energy on the order of many times the current total annual energy production of Earth. The electrical output of an entire planet for a year, for one ship during a single acceleration phase. That cost does not gradually improve with technological evolution in the way one might hope. The Lorentz factor demands a specific amount of energy to reach a specific speed for a given mass. What technology can change is efficiency. How well stored energy is converted into thrust, how much residual energy is lost, how completely energy is extracted from fuel. Better engineering can approach the theoretical limit. It cannot exceed it. It was Albert Einstein who discovered in 1905, upon publishing the special theory of relativity, something no one expected and that took decades to be fully accepted. Speed affects time. Not metaphorically, not as a philosophical statement about the subjectivity of experience. Physically, measurably. The faster you move through space, the slower time passes for you compared to everything you left behind. This is called time dilation, and it is one of the most thoroughly verified predictions in all of physics. GPS satellites orbiting Earth experience this. Without corrections for relativistic time dilation, GPS systems would accumulate positioning errors of several kilometers per day. The system would become useless within hours of operation. The correction is built into every satellite in the constellation because the effect is real and the equations are precise. If those equations were wrong, the navigation app in your pocket would be off by several kilometers by early afternoon. It is not. Particle accelerators demonstrate time dilation every single day. Muons are unstable subatomic particles with a half-life of about 2.2 microseconds. They are created in the upper atmosphere when cosmic rays strike air molecules at roughly 15 kilometers of altitude. the precision of the Lorentz factor deserves closer examination, not because it is an impressive number, but because of what that precision implies. The factor is not approximate. It is not a general guide. It is an exact mathematical relationship that has been verified at every speed and energy scale accessible to experimentation. When a muon survives its journey through the atmosphere longer than its half-life should allow, the Lorentz factor predicts exactly how much longer it survives, not approximately, exactly. When atomic clocks are flown on aircraft and compared to clocks left on the ground, the time difference is exactly what the Lorentz factor predicts. When particle accelerators measure the behavior of particles moving at 99.9% of the speed of light, the particles behave exactly as the Lorentz factor says they should. The agreement between theory and measurement across nearly 9 decades of experimental physics is not suggestive. It is definitive. What this means for the journey we are describing is that we are not extrapolating from a theory that might be wrong. We are applying a confirmed physical law to a new set of conditions. The numbers for a 1 light-year trip, the 52 days of crew aging at 99% of the speed of light, the year plus of time on Earth, are not predictions that could turn out differently when tested. They are the results of applying verified physics to the specific parameters of the trip. The universe has already told us how time behaves at these speeds. We know the answer. We have simply not yet made the journey. This carries a philosophical consequence that is rarely appreciated in full. A human being can describe with quantitative precision what happens on a trip no human being has ever taken. We can calculate how much each member of a hypothetical crew will age while Earth ages faster. We can calculate what colour the sky will be at 90% of the speed of light. We can calculate the accumulated radiation dose per month in interstellar space. This knowledge genuinely exists, tested and verified, built from experiments conducted here on one planet, by people who have never come close to these speeds. Physics has been able to go where bodies have not yet gone. At the speeds they travel, very close to that of light, they should deteriorate long before reaching the ground, given how short their half-life is and how far they need to travel. A simple multiplication says they should vanish before coming anywhere near sea level. They do not vanish. At Earth's surface, they are present in numbers that only make sense if time has slowed down for them. During their descent, it has slowed. The Lorentz factor predicts exactly how many survive the trip. The prediction matches the observation every single time experimenters have checked. This is not interpretation. It is a number and a measurement that agree to the precision of the instruments used. The intuition Einstein followed in 1905 came from a question that seemed simple, but had never been adequately answered. What does it mean for 2 events to happen at the same time? If you're standing still and 2 lightning bolts strike the ground a few meters apart and hit simultaneously from your perspective, does someone moving relative to you agree they were simultaneous? Newtonian physics assumed yes. Of course they are simultaneous, time is time, the same for everyone. Einstein showed that the answer is no. 2 events that are simultaneous for a stationary observer are not simultaneous for an observer in relative motion. The simultaneity of events is not absolute. It depends on the observer's state of motion. This is not a philosophical statement about perception. It is a physical statement about the nature of time. Time is not a universal river flowing at the same rate everywhere. It is a local property of the observer. Every object, every person, every clock carries its own version of time, and those versions run at rates determined by how fast that object is moving and how deep it sits in a gravitational field. The consequence for travel is that 2 clocks synchronized at the same location and then separated, one staying still, one moving at high speed, will no longer agree when reunited. The moving clock will have recorded fewer seconds. This was confirmed with atomic clocks on airplanes. Clocks flown around the world tick slightly slower than those left on the ground. The difference is minuscule, nanoseconds, but it is real, measurable, and it matches the prediction of special relativity exactly. Scale that experiment up to a ship crossing a light year at 99% of the speed of light, and the difference is not nanoseconds. It is weeks. The physics is the same, only the scale is different. There is a quantity physicists call the Lorentz factor. It describes how much time slows down for a moving object relative to a stationary observer. At everyday speeds, the factor is so close to 1 that the time difference is a few nanoseconds over an entire lifetime of motion, irrelevant for any practical existence. But as you approach the speed of light, the factor climbs. At 10% of light speed, it is just above 1.05. Time passes about 0.5% slower for you than for stationary observers, real but small. At 50% of light speed, it is about 1.15. For every year you experience, 1.15 years pass on Earth. At 90%, the factor reaches approximately 2.3. For every year you age aboard, 2.3 years pass outside. At 99%, it jumps to about 7.1. For every 7 years that pass on Earth, you personally live one. At 99.9%, the factor reaches approximately 22. For every year you experience aboard, 22 years pass everywhere else. This has a concrete consequence for a 1 light-year journey. A ship travelling at 99% of the speed of light takes about 1 year and 13 days to cross 1 light-year measured on Earth. That is what an external observer on Earth would measure. But for the crew inside the ship with the factor at 7.1, they age only about 7 weeks. They depart. They cross the entire distance. They arrive at their destination, and they have personally experienced about 52 days. Meanwhile, back on Earth, more than a year has passed. Families are older. Events have occurred. The world has moved forward at a pace completely independent of what was happening aboard that ship. This is not an approximation. It is not a philosophical thought experiment about subjective time. It is what the equations predict, what every experimental test at every accessible scale confirms, and what would in fact happen. The universe keeps separate clocks for things moving at different speeds. Speed is the dial that controls how much those clocks diverge, and the divergence, once it has occurred, is real and cannot be reversed. You cannot go back and resynchronize. You have lived different amounts of time. That is the situation. The visual experience of travelling at relativistic speed is completely different from anything any film has ever shown. We do not need to speculate about what you would see. We can calculate it. The first visual effect is the Doppler shift. You have encountered this with sound. An approaching vehicle has the noise of its engine compressed into a higher pitch. As it passes and moves away, the pitch drops. Sound waves are compressed ahead of the vehicle's motion and stretched behind it. Light behaves the same way because light is also a wave. When you are moving toward a source of light at a significant fraction of the speed of light, the wavelengths of that light are compressed. The light shifts toward shorter wavelengths, toward blue, toward violet, and at extreme speeds into ultraviolet and beyond. When you move away from a source, its wavelengths stretch toward red and then into infrared. At 10% of a light speed, the effect is noticeable but subtle. Stars in the forward direction appear slightly bluer than normal. Stars behind appear slightly redder. The sky still looks broadly familiar. At 50% of light speed, the shift is pronounced. Stars ahead that were yellow now appear blue-white. Stars that were orange-red now look yellowish. The forward hemisphere of the sky has a visibly different palette from the one you knew. At 90% of light speed, the Doppler shift is extreme. Visible light from stars directly ahead has been compressed into ultraviolet frequencies, wavelengths your eyes cannot detect. Stars that were luminous and visible have effectively vanished from your perspective. Their light shifted entirely beyond your visual range. What replaces them in the visible spectrum is the infrared light from cool, faint stars that were nearly invisible from Earth, now shifted into wavelengths your eyes can register thanks to your speed. The sky ahead is populated by different stars from the ones you knew from Earth. Stars that were invisible before, in a different arrangement, a different sky. The second visual effect is called relativistic aberration. At rest, stars are distributed across the entire sphere of the sky. in the pattern your star charts show. When you begin moving at relativistic speed, the geometry of incoming light changes. Stars that were off to the side appear shifted toward the direction of motion. Stars that were behind you creep forward. The faster you go, the more extreme the compression becomes. At 50% of light speed, the entire night sky appears squeezed toward the forward hemisphere. The rear half of the sky looks noticeably emptier than normal. At 90% of light speed, nearly all the visible stellar content of the universe has been swept into a cone covering about 26 degrees ahead of you. Stars that should be to your left, to your right, behind you, all compressed forward by your motion. The sky in other directions has gone almost black. At 99% of light speed, that cone has narrowed even further. Virtually all visible starlight crowds into a tight ring around a point directly ahead. Behind you, near complete darkness. Not because there is nothing there, but because the light from everything in those directions has been bent forward by your speed. The physics of wave propagation and motion does not care whether you preferred the stars to stay where you expect them. They move. There is a haunting beauty in all of this if you pause to consider it. The sky you would see from inside a ship travelling at 99% of the speed of light would not merely be different. It would be a sky no human eye has ever seen. An arrangement of light that exists at no fixed point in the universe, that exists only in relation to you and your specific speed, that would change with every second you accelerated or decelerated. It is a phenomenon you would carry with you like a signature of your trajectory, and when you stopped, when the speed dropped back to zero, that particular sky would vanish. It would never exist in exactly the same form again for anyone. The universe does not keep that record. You are the only possible observer of a sky that exists solely in your relationship with the space you're crossing. And it is not only starlight. The cosmic microwave background, the residual glow from the early universe, normally distributed uniformly across the entire sky at a temperature of about minus 270 degrees Celsius, also shifts toward blue ahead of you with your speed. Normally, this radiation is completely invisible to human eyes. It exists at microwave frequencies far below what you can see, but at 99% of the speed of light, it has been compressed into visible and ultraviolet wavelengths. The forward arc glows with it, light with no particular star as its origin, but coming from the oldest light in the universe, the relic radiation of the Big Bang itself made visible by the speed you are travelling. Standing at the forward viewport of a ship crossing a light year at near light speed, what you would see would be unlike anything any human has ever witnessed. A bright ring of compressed light ahead, near darkness almost everywhere else. Stars you never saw before because they were previously in the infrared. Stars you expected to see gone because their light was pushed beyond your visual range. The universe rearranged by your speed into something entirely new. There is a physical fact about interstellar travel that nearly everyone overlooks when imagining it. Space is not empty. Between the stars there is gas and dust. The interstellar medium, a thin distribution filling the galaxy. On average, about 1 atom per cubic centimetre in typical interstellar regions, mostly hydrogen, the simplest and most abundant element in the universe, about 10% helium by number, traces of carbon, oxygen, nitrogen, iron, and other heavier elements, scattered remnants of stars that lived and exploded before our solar system formed, and scattered throughout, microscopic dust grains, particles of silicate minerals and carbon compounds typically ranging from nanometers to micrometers in size. By any laboratory standard, this is an extreme vacuum. The best vacuum chambers on Earth contain several 100 million atoms per cubic centimetre. Interstellar space has one. To put it in perspective, the best vacuum we can achieve in a laboratory is still about 100 million times denser than typical interstellar space. At low speeds, this thinness is completely irrelevant to a spacecraft. Voyager 1 has been travelling through interstellar space for over a decade. Its instruments still work. One hydrogen atom per cubic centimetre presents no practical problem at 70,000 km per hour. That changes completely at relativistic speed. At 10% of light speed, the kinetic energy of a single hydrogen atom striking the bow of the ship, measured in the ship's reference frame, is approximately 400 million electron volts. That is the energy range of high-energy cosmic rays, exactly the same particles space agencies worry about when planning long-duration missions. At typical interstellar densities, the bow encounters on the order of several hundred atoms per second per square metre of frontal area. Each collision individually deposits a small amount of energy, but collectively, over months and years of travel, those collisions accumulate. They heat the hull material. They create radiation damage in the molecular bonds of whatever the hull is made of. They produce secondary particles, fragments of shattered atomic nuclei that propagate inward through the material. At 90% of light speed, the situation becomes severe. Each hydrogen atom the ship encounters now carries, relative to the ship, about 1,200 million electron volts of kinetic energy. A ship at 90% of light speed flies bow first into a continuous low-flux version of that particle beam. The hull does not distinguish whether it is a fast proton hitting a stationary wall or a stationary wall hitting a fast proton. They are physically identical situations, and the damage at these energies is not negligible. High-energy protons striking metal can shatter atomic nuclei, producing cascades of secondary particles. The shielding needed to protect crew members from the interstellar medium at 90% of light speed would need to be substantial. Meters of dense material at the forward edge of the ship. Water is among the better practical choices because hydrogen nuclei absorb high energy, particle radiation more efficiently without generating as many harmful secondary particles as metals do. The problem with water is mass. Meters of water is a very large amount of mass, and mass is the central problem to which everything in interstellar design inevitably returns. There is also a hazard that rarely appears in discussions of interstellar travel: dust. Not metaphorical dust, not astronomically aggregated dust. Real, microscopic dust. The grains of matter that exist in the interstellar medium alongside hydrogen atoms. At a speed of 10% of light speed, a particle with the mass of a single grain of sand, about 1 milligram, strikes the ship's hull with kinetic energy equivalent to more than 100 kilograms of conventional explosive. This is not metaphor or exaggeration for dramatic effect. It is the number. At 20% of light speed, that same grain delivers the equivalent of several hundred kilograms. At 50% of light speed, several thousand kilograms equivalent. The damage mechanism at these speeds is completely different from what one would expect of a conventional impact. At relativistic impact speeds, both the projectile and the material it hits essentially vaporize instantly on contact. The kinetic energy converts to heat so rapidly that matter passes directly from solid state to plasma. The result is a jet of superheated plasma expanding from the impact point at enormous velocity. Current spacecraft use Whipple shields, a layered defense separated by a gap, which works reasonably well for micrometeorites in the inner solar system. At relativistic impact energies, standard Whipple shields are inadequate. The engineering of protection against dust impacts is, by itself, a field of research that still lacks definitive solutions for the speeds interstellar travel demands. The energy required to move mass at relativistic speeds is one of the most important physical facts about interstellar travel. The relationship is not linear. At everyday speeds, kinetic energy scales in a way that is at least intuitively comprehensible. As you approach the speed of light, the relationship changes fundamentally. The energy needed to gain additional speed grows according to the same factor that dilates time, the Lorentz factor. That factor approaches infinity as speed approaches the speed of light. At 50% of light speed, you need to supply energy equivalent to about 15% of the ship's rest mass energy to set it in motion at that speed. At 90% of light speed, about 130% of the rest mass energy is required. Rest mass energy is the energy equivalent of the ship's mass, from the equation E equals m times c squared. For a ship large enough to carry a crew with life support, radiation shielding, food, water, medical supplies, navigation systems, communication equipment, spare parts, the total mass would be at minimum several thousand kilograms, probably far more. And then you need to decelerate at the destination. The same cost again. The most energy-dense fuel conceivable is antimatter. When a particle of matter meets its corresponding antiparticle, they annihilate completely. 100% of their combined mass converts to energy, exactly as E equals m times c squared describes. 1 kilogram of antimatter annihilating with 1 kilogram of ordinary matter releases an amount of energy that has no analogue on the human scale. Nothing in all of physics can match that energy density. It is the theoretical ceiling, the absolute maximum available from any given mass of fuel. And even with perfect antimatter fuel, the mass ratios for a brute interstellar ship at high relativistic speed are merciless. The Tsiolkovsky rocket equation, published in 1903 by the Russian mathematician Konstantin Tsiolkovsky, and as inflexible today as it was then, describes the fundamental relationship between propellant mass and the change in velocity it produces. At relativistic speeds, the relationship worsens. To accelerate a ship carrying even 1,000 kilograms of payload to 90% of light speed and then stop it at the destination, far more than 2,000 kilograms of antimatter is needed, because you must also accelerate the fuel, and the fuel for the fuel. The rocket equation compounds the way compound interest compounds, except much faster and in the wrong direction for mass fraction. The result is that the vast majority of the ship's mass at launch would need to be fuel. A small fraction would be the actual payload, the people and the equipment they need to survive, and we cannot produce antimatter in any quantity approaching what is needed. The combined output of every particle accelerator on Earth produces nanograms of antimatter per year. A nanogram is 1/billionth of a gram. An interstellar mission using antimatter fuel would require kilograms, possibly tons. The gap between what we can produce and what would be needed is about 10 orders of magnitude. This is not a gap engineering can close with gradual improvements. It requires physics we do not currently possess, at scales we cannot reach. In the late 50s and early 60s, the United States government funded serious engineering work on a propulsion concept that sounds extreme until you realize it was based entirely on existing technology, propelling a spacecraft by detonating nuclear bombs directly behind it. A massive shock absorber plate at the rear of the ship would capture the impulse from each explosion. Several detonations per second would accelerate the vehicle. The bombs existed. The absorber engineering was worked out. Freeman Dyson, one of the most formidable physicists of the 20th century, calculated trajectories and performance in detail. Project Orion was not fringe science. It was a serious engineering effort conducted by serious physicists and engineers using real calculations and real hardware. Large Orion vehicles could theoretically reach a few % of the speed of light. The project was ended by the Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear detonations in space. Not by physics, not because the concept did not work, by politics. Project Orion is a data point. It shows that the gap between what we can build today and what interstellar travel demands is not absolute. Every serious interstellar propulsion concept that has been rigorously evaluated, Orion, Project Daedalus, laser sails, magnetic sails, identifies real physics that could in principle deliver significant performance. None is ready. None approaches the full requirements, but all point in the same direction, toward physics that works, away from what does not. Think carefully about deceleration, because it is the half of the problem most discussions underestimate. Assume you have solved propulsion. You have found the energy, built the engines, accelerated your ship to 90% of light speed. You are crossing a light year. You are going to arrive somewhere and you need to stop. There is no brake that works in deep interstellar space. No air resistance, no runway, no medium to push against in any useful way. The interstellar medium creates so little drag that it is a navigational correction over years, not a meaningful deceleration force. The only way to slow from 90% of light speed is to fire your engines in the direction of travel, push yourself backward against the motion, and sustain that thrust until the speed drops to something manageable. This consumes the same amount of energy as the acceleration phase. If you carry fuel for both legs, the initial launch mass grows substantially. The fuel for deceleration must be accelerated during the outbound trip, which requires more fuel to accelerate the deceleration fuel. The rocket equation compounds again. One-way missions have simpler energy budgets than round trips, which is part of why serious proposals for the first interstellar missions involve one-way travel. You pay the acceleration cost only once, but one-way means no return. The first humans to leave the solar system permanently, knowing they will not come back, accepting that as the price of going. The physics is more tractable. Everything else is harder. There is also the question of what happens to the ship in transit when it is neither accelerating nor decelerating but simply cruising through interstellar space. The kinetic energy the ship carries at that point is enormous. At a speed of 10% of light speed, a 1,000-ton ship carries kinetic energy equivalent to more than 100 megatons of explosive. That is not the fuel on board. That is just the motion itself, the energy of the body in transit. A structural failure that caused significant disintegration at that speed would not produce debris floating in space. It would produce fragments, each carrying enormous kinetic energy, continuing on roughly the same trajectory at roughly the same speed. Planning for gradual degradation rather than catastrophic failure, ensuring that system failures cannot propagate in ways that cause disintegration at speed, is a constraint that exists for no other form of transport. Engineers validate designs through analysis and component testing at accessible speeds, then apply those models to the full-scale scenario at full speed. The safety margin for error is not generous. Now step inside the ship and consider what happens to the human body. The human body evolved over millions of years to function under a specific set of conditions: a gravitational field of approximately 9.8 meters per second squared, an atmospheric pressure of about 101,000 pascals at sea level, a radiation shielding environment provided by Earth's magnetic field, and several dozen kilometers of atmosphere overhead. Every system in the body, skeletal, muscular, cardiovascular, neurological, immune, hormonal, sensory, was shaped by millions of years of evolution under those conditions. Remove them and the systems adapt. But biological adaptation does not mean improvement. It means optimization for the new environment, and the new environment is not the one your biology was built for. Start with gravity. On a ship at constant velocity through interstellar space, there is no effective gravity. Everything floats. That feels unusual for a few minutes and pleasant for a few hours. Over days and weeks, it begins to become a systematic dismantling of the body. Bone is not dead structural material like steel or concrete. It is living tissue in constant dynamic remodeling. Specialized cells called osteoblasts build new bone by depositing calcium phosphate mineral into a protein matrix. Other cells called osteoclasts break bone down, dissolving the mineral back into the bloodstream. On Earth, the mechanical stress of standing and walking provides the signal that tells osteoblasts to maintain their pace, to keep building bone at the same rate it is being broken down. Without that signal, the balance tips. Osteoclasts continue their work at the normal rate. Osteoblast activity declines. Bone density drops. The rate is about 1 to 2% of mineral density per month in the most affected regions. The weight-bearing bones of the spine, hips, and upper legs. Astronauts on 6-month missions aboard the International Space Station lose an average of 10 to 15% of their bone mineral density. Their skeletal systems are measurably weaker after half a year. Not metaphorically weaker, measurably, quantifiably weaker in ways that show up on bone density scans. Recovery after returning to Earth takes many months of weight-bearing exercise and physical therapy. Some density loss is never fully recovered. Extend that not to 6 months, but to the years a 1 light-year journey at 10 or 20% of light speed would require. The people who would have to find out what happens are the ones inside the ship, years away from anyone who could help in a medical situation with no established treatment protocol. Muscle follows identical logic. On Earth, simply standing upright requires continuous low-level muscular work. The postural muscles, the deep muscles of the back, the core, the legs fire continuously to prevent collapse. In microgravity, that demand disappears. Muscles that evolve to work against gravity have no load to work against. They atrophy rapidly. Astronauts on the International Space Station follow mandatory daily exercise protocols, 2.5 hours of structured resistance training and cardiovascular exercise every day. Not optional, not recommended, required by mission rules. And despite those mandatory 2.5 hours, they still lose up to 20% of muscle mass on a 6-month mission. Exercise slows the atrophy. It cannot stop it. The cardiovascular system adapts to microgravity in equally problematic ways. On Earth, the heart pumps blood upward against gravity to reach the brain. In microgravity, there is no upward. Blood does not pool in the legs the way it normally does. Fluid redistributes toward the head and chest, a condition astronauts frequently describe as feeling like they have a permanent cold, with puffy faces and nasal congestion. The body, sensing elevated pressure in the upper body, interprets it as excess fluid and begins excreting it. Blood volume decreases. The heart, no longer fighting gravity to reach the brain, does not need to work as hard. It adapts over weeks and months, becoming slightly smaller, remodeling itself for a less demanding workload. That adaptation is appropriate for the environment the heart is actually in, but it is the wrong adaptation for a return to gravity. Astronauts returning from 6-month missions frequently need assistance to exit the spacecraft. Their cardiovascular systems have deconditioned to the point where having to pump blood upward against gravity again is a shock. Standing causes blood pressure to drop. The brain does not receive adequate flow. People faint. Reconditioning takes weeks of gradual re-exposure. After years of microgravity, the deconditioning would be far more profound. About 60% of astronauts who spend extended time on the International Space Station report visual changes after their missions. Many are subtle, some are significant, some are permanent. The most likely explanation involves intracranial pressure, the pressure of the fluid surrounding the brain and optic nerves. Without gravity pulling fluid toward the feet, the normal distribution of cerebrospinal fluid changes. More fluid accumulates around the brain and optic nerves. The elevated pressure can cause swelling of the optic disc, the point where the optic nerve meets the retina inside the eye. It can also subtly deform the eyeball itself, altering its focal distance. The most common result is a shift toward farsightedness. Some reversal occurs after returning to Earth, some does not. There are astronauts with permanently reduced visual acuity after 6-month missions. The immune system also changes in microgravity, and the changes do not go in a useful direction. Immune cells exhibit reduced functional capacity in microgravity. Their proliferation is impaired. Their ability to recognize and respond to pathogens is diminished. Several viruses that healthy immune systems normally keep suppressed show signs of reactivation in astronauts on longer missions. The Epstein-Barr virus, which causes mononucleosis and is present in most adults in a latent state. The varicella-zoster virus, which initially causes chickenpox and then remains latent, capable of reactivating as shingles. Cytomegalovirus, another virus from the herpes family that remains latent in most infected people. In astronauts, these viruses become detectable at elevated levels in saliva and other body fluids during missions. The immune system is suppressing them less effectively. Over a voyage of several years, in a small crew living in a closed, self-contained habitat, that immune suppression deepens with time, and medical care is whatever was brought aboard the ship. There is no hospital, there is no physician outside the crew, no specialist to evacuate to. Every medical event is managed with the training and supplies on board. with communication delays of months to years for any guidance from Earth. There is also a dimension of microgravity effects that more recent research has taken seriously, and that for a long time remained outside mainstream discussions. What happens to brain tissue during prolonged exposure? The brain is protected by a fluid that circulates around and within it, the cerebrospinal fluid. On Earth, this fluid distributes differently when you're standing, sitting, or lying down, because gravity pulls the fluid downward in each position. In microgravity, there is no positional difference. The fluid distributes uniformly around the brain in ways that terrestrial physiology never requires. Over weeks and months, this continuous redistribution can alter the internal pressure within the skull in ways that imaging studies of astronauts have begun to document. Some of these changes are subtle, some are not. The volume of certain brain regions changes measurably after long-duration missions. The fluid dynamics around the brainstem are altered. The question of whether these changes affect cognitive function and to what degree is an active area of research. The existing data are sufficient to raise genuine concern but insufficient for a definitive answer, and the definitive answer can only come from exposures longer than any astronaut has experienced so far. High-energy cosmic rays have yet another effect that deserves separate mention. A heavy, high-energy particle, a carbon nucleus, an iron nucleus, a silicon nucleus, moving at near-light speed, passing through brain tissue does not merely cause diffuse chemical damage through ionization. It causes physical disruption along the particle track. Axons can be severed. Myelin sheaths can be damaged. Neurons along the track can be physically destroyed in ways the body's normal cellular repair mechanisms do not easily fix. Animal studies using heavy ions similar to galactic cosmic rays have documented measurable cognitive effects at doses relevant to long-duration spaceflight, impaired spatial memory, reduced performance on problem-solving tasks, increased anxiety and reduced behavioral flexibility, changes in the ability to learn new tasks. These are not subtle population-level statistics barely reaching statistical significance. They are measurable changes in the behavior of individual animals, and the cognitive functions most sensitive to heavy ion radiation are precisely the ones most needed on an interstellar mission. Complex reasoning, adaptive problem-solving, spatial navigation, decision-making under novel and high-risk conditions. The radiation environment works against those capabilities over time, not as a certainty, but as a growing probability. With each additional year of exposure, the weight of that risk increases, silently and mathematically without pause. There is also the question of galactic radiation, which deserves its own careful attention. In interstellar space, far from Earth, far from any stellar magnetic field, far from any atmosphere, the radiation environment is constant and arrives from all directions simultaneously. The primary threat is galactic cosmic rays, high-energy particles, predominantly protons but also heavier atomic nuclei stripped of their electrons, accelerated to near light speed by violent astrophysical events scattered across the galaxy and beyond. Supernovae accelerate particles at expanding shock fronts. Pulsars, rapidly spinning neutron stars with extraordinarily intense magnetic fields, accelerate particles with those fields. Active galactic nuclei contribute particles at the highest energies. These particles travel through the galaxy for millions of years, bouncing off magnetic field lines and magnetic irregularities, losing relatively little energy during that wandering journey. They arrive at any point in space from all directions continuously without pause at all times. On Earth, two shields handle this. The magnetic field deflects most charged particles before they reach the atmosphere, and the atmosphere absorbs the secondary particles produced when cosmic rays enter it. In interstellar space, neither of those shields exists. The hull of the ship is all that stands between the crew and that constant radiation, and the hull, to be protective enough, would need meters of dense material surrounding the crew compartment, which has direct implications for the mass problem we already discussed. Every additional meter of shielding is more mass to accelerate, more fuel needed, more energy demanded. The psychological dimension of an interstellar voyage is a challenge that runs parallel to the biological ones and is no less severe. Human beings evolved in social environments. Our ancestors lived in groups. Survival depended on community, on the exchange of resources, information and support that only groups provide. Our psychology is calibrated for a world with other people. Remove that environment and human psychology responds, not catastrophically in every case, but measurably and reliably. Research on isolated and confined environments, winter stations in Antarctica, submarine crews on long patrols, space station crews, provides a consistent picture of psychological changes over time. Mood destabilizes during prolonged isolation. Interpersonal conflicts, which in normal social environments are diffused by the presence of many people and the ability to seek different company, concentrate and intensify in small groups with no exit. Cognitive functions associated with emotional regulation can become less effective over months of confinement. Performance on tasks requiring sustained attention degrades in statistically significant ways. Sleep quality tends to deteriorate in isolated and confined environments, particularly when natural light cycles are absent or disrupted. And the particular character of interstellar isolation adds dimensions that isolation in Antarctica or on submarines does not have. Communication with Earth degrades continuously. It is not simply that contact is limited from the start. The connection actively worsens. Each month the signal delay grows. Each month what arrives from Earth is older. The crew watches, in real time and in slow motion, the communication link with everything they knew, thinning toward uselessness. 6 months into the voyage, responses from Earth arrive weeks after the questions were sent. A year in, it is months. At 5 years of travel, the delay is half a year in each direction. Nothing happening on Earth right now can be known aboard the ship for 6 months. The world they left continues without them, in ways they can only discover with enormous delay. People they care about go through experiences good and difficult, and the crew learns of those events long after the fact. Consider specifically what communication at 1 light-year means for a crew member trying to maintain any relationship with people back on Earth. You send a message, you describe what happened today, what you're thinking, how you are. That message travels at the speed of a light, the maximum speed anything can move, and arrives on Earth 1 year later. The person you care about reads a description of who you were and what you experienced a year ago. They write back immediately. They describe their life, their thoughts, their current situation. The reply travels back at the speed of light. It reaches you 1 year after being sent, 2 years after you sent your original message. 2 years after sending your original message, you receive a reply. You are reading about what their life was like a year ago, written in response to what your life was like a year before that. The exchange is real. The care is real. The words are genuine. But you are both responding to each other's past selves. The conversation is always conducted across a gap. Any statement you make is about a situation that has been resolved, changed, or evolved long before the reply arrives. Any reply you receive addresses a version of you that no longer exists in quite the same way. The emotional weight of this, accumulated over years, is a genuine challenge that current research on isolated environments can identify, but not fully characterize because the delay itself is a new variable. The most reliable solution to most microgravity problems is artificial gravity through rotation. This is not exotic technology, it is basic physics. A rotating structure creates centripetal acceleration that is physically indistinguishable from gravity for anyone standing on the inner rim. The cardiovascular system, the skeletal system, the vestibular system, the immune system respond as they would to gravity. The engineering challenge is making it work at the right scale and rotation rate. The human vestibular system can tolerate rotation of up to about 2 revolutions per minute without producing significant disorientation. Above that rate, the Coriolis effect becomes noticeable. To produce 1 g of effective gravity at 2 revolutions per minute, a rotating ring needs a radius of about 225 meters. It is not physically impossible. Several credible engineering studies over several decades have proposed rotating habitats at that scale. The designs are complex, but not based on unknown physics. The problem is that it adds mass, and mass is the thing the energy problem is most sensitive to. The solution to the biology problem imposes additional costs on the energy problem. These two challenges are not independent. Solving one makes the other harder. That is the pattern running through all interstellar engineering. The problems interconnect. Every solution has costs. Every cost has consequences. The universe enforces that consistency. In 1978, the British Interplanetary Society published the Daedalus study, a 2-year engineering feasibility assessment for an uncrewed interstellar probe. The target was Barnard's star, about 6 light-years away. The proposed vehicle would use inertial confinement fusion, small pellets of deuterium and helium, 3 compressed by electron beams at 50 shots per second. The vehicle would reach 12% of light speed. The one-way trip to Barnard's star would take about 50 years. The mass budget, around 54,000 metric tons at launch. The helium-3 requirements, the fuel for the first stage, would require mining the atmosphere of Jupiter. Not because the designers were being unrealistic, because physics demands it. That is how much fuel a fusion engine needs to push 54,000 metric tons to 12% of light speed. The Daedalus study is remarkable not because it solved the problem, but because it characterized it. It showed, with rigorous engineering calculation rather than vague speculation, what the requirements are. The Breakthrough Starshot initiative, funded in 2016, aimed at a different approach. Tiny light sails propelled by an array of ground-based lasers to 20% of light speed, in recognition that the mass problem is the central problem. Make the ship small enough and the energy requirements drop from impossible to merely extremely difficult. Each of these projects is a different engagement with the same physical constraints. The constraints do not change. What changes is the seriousness with which people try to work within them. Physics does not charge less for being approached with more creativity. It charges the same, always. But creativity changes what is possible to build within what it charges. And that difference over decades and generations is the difference between the impossible and the merely extremely difficult. The return trip, if there is one, adds its own layer to all this temporal displacement. You travel 1 light year away at 99% of light speed. You experience 52 days. You stop at the destination. You spend some time there, days, weeks. You accelerate back toward Earth at 99% of light speed. You experience another 52 days on the return journey. You arrive on Earth approximately 2.5 years after you departed. Measured in Earth time, you have aged about 110 days. Your friends have aged more than 2.5 years. A child who was 10 when you left is now 12.5. A parent who was in good health when you launched has gone through more than 2 years of aging. The cognitive dissonance of returning to a world that moved forward without you, a world 2.5 years older while you're only 3.5 months older, is not a simple thing to process. You're the same person. The relationships you had before leaving are still real, but the shared timeline has fractured. You and the people who love you lived through the same 2.5 years of history, but at different rates. You experienced a slice of it. They experienced all of it. The gap is permanent. It cannot be repaired by conversation or explanation. It can only be acknowledged as the physical consequence of the journey you chose to make. The universe does not make exceptions for emotional attachment. It applies the Lorentz factor uniformly, without regard for what it costs the people on either side. There is something that deserves recognition about what the act of calculating this journey reveals. We are capable of describing with precision a trip we cannot take. We can state every consequence of crossing a light year, the exact time dilation, the exact radiation dose, the exact Doppler shift, the exact energy cost with quantitative precision. We can know in detail what would happen to human biology on a decade-long trip at 10% of light speed. We can know what the sky would look like at 99% of light speed. Calculate the aberration angle. Predict which stars would shift into visible wavelengths from the infrared. describe the exact hue of the compressed cosmic microwave background. All of this knowledge exists. None of it was gathered from someone who made the trip. It was assembled from 4 centuries of physics developed here on the ground, from Galileo and his inclined planes to the Large Hadron Collider. From observations of phenomena, the equations predicted before those phenomena were detected. Gravitational waves, black holes, cosmic microwave background polarization, orbital decay of binary pulsars, from experimental verification of time dilation in particle accelerators and atomic clock experiments, from half a century of human spaceflight, continuously refining our understanding of how biology responds to the space environment, from satellite operations that depend on relativistic corrections being exactly right, from robotic probes in interstellar space, the Voyagers providing direct measurements of the environment beyond the heliopause, all assembled into a picture detailed enough to describe in advance what would happen to a crew crossing a light year. This is no small thing. It is science operating at its highest level, building knowledge systematically over centuries until it describes phenomena beyond the reach of any individual or generation to observe directly. Think about what it means to be the generation that builds the first interstellar capability, not the generation that crosses a light year, the generation that achieves the propulsion, the biological management, the shielding, the power generation that makes the crossing possible. That generation will not be the one that goes. The engineers who solve the propulsion problem may not live to see the mission launched. The biologists who work on long-term physiological countermeasures may not see the crew they helped keep alive. This is not unique to interstellar travel. The physicists who developed the theoretical foundations of nuclear energy died long before the technology reached its current scale. The mathematicians who formulated the equations of orbital mechanics lived centuries before the first spacecraft flew. Science builds across generations. Knowledge does not belong to the people who generated it. It belongs to everyone who comes after. Navigation across a light year demands its own separate consideration. You're not following a road. There are no fixed landmarks in any conventional sense. Every reference point you could use is itself in motion. Stars orbit the galactic center. The Sun orbits at approximately 800,000 kilometers per hour, completing one circuit in about 225 million years. Other stars orbit on their own paths at their own speeds and orbital inclinations. Over the years of an interstellar voyage, the positions of surrounding stars shift measurably relative to where they appeared at departure. Navigating to a destination requires knowing where it will be when you arrive, not where it appears from Earth now, not where it was when the mission was planned, but where it will be at the exact moment of your arrival. For nearby stars, we have that data. The Gaia mission, a European astrometric satellite launched in 2013, measured positions, proper motions, and distances of about 1.8 billion stars with extraordinary precision. Position predictions for stars within 100 light-years are accurate enough to serve as navigation targets on timescales of several years. For absolute position determination without communication with Earth, pulsar timing offers the most reliable method available. Millisecond pulsars, neutron stars spinning hundreds of times per second, emitting beams of radio or X-ray emission that sweep past us with extreme regularity, serve as cosmic clocks. Their timing is stable to parts per quadrillion. By measuring the arrival times of signals from multiple pulses simultaneously, and comparing those times with precisely calculated predicted values, a ship can determine its three-dimensional position in the galaxy with high accuracy. Of all the challenges of interstellar travel, navigation is perhaps the most tractable. It is a problem of precision and computation. Physics does not actively work against you the way it does with energy and biology. We are currently the people who come after several centuries of physics development. The understanding we have of what a light year demands comes from thousands of people over hundreds of years who asked precise questions and recorded precise answers. We did not generate the physics ourselves, we inherited it. The next generation inherits what we add. The next step from this place is not the crossing. It is the slow, patient, and ruthlessly honest widening of possibilities within the constraints physics allows. Here is what we have without having made the journey. We know time dilation at every speed. We know the Doppler shift that transforms the apparent colour of every star. We know the aberration effect that gathers the light of the universe forward. We know what the interstellar medium does to a hull at 10, at 50, at 90% of light speed. We know the rate of bone loss in microgravity from 6-month missions. We know radiation dose rates in deep space and their cumulative biological effects. We know the communication delay at every point along a 1 light-year route. We know the navigation mathematics and pulsar timing methods that make positioning possible without contact with Earth. We know what time dilation means for the crew and for the people left behind. None of this knowledge comes from having made the journey. It comes from physics developed over 4 centuries, tested in laboratories, particle accelerators, atomic clocks, and orbiting satellites. From observations of phenomena the equations predicted before those phenomena were observed. Muons decaying at exactly the rate the Lorentz factor says. GPS clock drift at exactly the rate relativity predicts. Gravitational lensing bending light exactly as general relativity calculates. Orbital decay of binary pulsars matching the prediction of gravitational wave emission exactly. The universe keeps returning the same answer because there is only one answer. Physics is not a working hypothesis. It is a description of how reality actually behaves. Every test, every measurement, physics is right. The GPS in your pocket depends on relativistic corrections calculated from the same equations that describe a 1 light-year trip. If those equations were wrong, the GPS would be wrong. It is not. The muons at Earth's surface are present in exactly the numbers the Lorentz factor predicts. If the prediction were wrong, the muon count would not match. It matches every time. Consider what the crew encounters after years of travel, after weeks of subjective time at high relativistic speed. You have crossed a light year, you're on the other side, and you are not in a star system. The nearest stars are still more than 3 light years away. Proxima Centauri, the closest star to the Sun, is 4.24 light years away. Alpha Centauri A and Alpha Centauri B, the 2 Sun-like stars around which Proxima orbits, sit at about 4.37 light years. 1 light year places you in the interstellar void between the solar system and the nearest stellar neighbours. In the middle of the gap, there is no planet, no moon, no asteroid belt, no atmosphere, no magnetic field offering any protection against radiation, no solar wind, no significant starlight for power. The sun behind you has shrunk to a bright stellar point, still the brightest in the sky by a substantial margin since you travelled directly away from it, but providing no usable warmth or energy at that distance. The ambient temperature of the environment approaches the temperature of the cosmic microwave background, about minus 270 degrees Celsius, just a few degrees above absolute zero. Every photon of heat inside the ship was generated internally, the reactor, the electronics, the biological warmth of the crew. Thermal balance management, keeping the interior at survivable temperatures, requires careful engineering of the hull and continuous power generation. In space, the only way to shed heat is through radiation. A surface at a given temperature radiates heat at a rate proportional to the 4th power of that temperature. The radiators on an interstellar ship need to be large enough to dissipate the ship's waste heat at a rate that keeps internal temperatures survivable, but radiators are mass, and mass, as has been established throughout this entire conversation, is the central problem nothing escapes. And here, at this point, 1 light year from Earth, is where isolation becomes more concrete than at any earlier part of the journey. A signal to Earth takes 1 year to arrive. A reply takes another year. Any news from Earth reflects the world of more than a year ago. If something goes wrong now, there is no rescue that could reach you in any time frame that would matter for an emergency. A rescue mission launched immediately upon receiving the distress call would take at minimum another year just to receive the call. Years to prepare and travel. Nothing could arrive in time for any acute crisis. You're on your own. The ship, the crew, the knowledge and supplies aboard. every decision made by the people present with what they have. There is no one else. This is what 1 light-year means as a distance, not a destination, but a demonstration of what the universe is made of and how much of it there is. Stars are rare. The space between them is the default state of the cosmos. The void is not an exception or an accident, it is the rule. It is where most of the universe has always been and always will be. And the fact that we can calculate every consequence of this crossing, the exact time the crew ages relative to Earth, the exact colour shift of the stars, the exact rate of bone loss, the exact energy cost, that is the product of 4 centuries of people asking precise questions and accepting precise answers, even when the answers describe a journey none of them could ever make, even when the answers are humbling. We know what it costs, we know what it does, we know what it looks like. We are ready to understand, and that is where every great journey begins. The sentences can start getting shorter now. While you rest, the light keeps travelling at 300,000 kilometers per second in every direction, without pause. The Oort Cloud wraps the solar system in silence, 1 light-year from you, in every direction. Physics does not sleep. The stars do not stop. The cosmos continues its dance, indifferent to the hour and the weariness of whoever watches. You are here, safe, in the only place in the universe that evolution built to hold you. The universe takes care of you. Everything is in order. While you rest, the light that left the sun 8 minutes ago is still travelling. The light that left Proxima Centauri 4 years and 2 months ago is arriving now. The light from the Big Bang, 14 billion years old, still fills the universe in every direction, compressed into frequencies you cannot see but that exist around you in this very moment. You are part of this. You always have been. Close your eyes gently. Good night. The universe continues its silent dance and we rest within its embrace. Thank you for walking with me tonight. Sleep well.